Wow. Did anybody else hear that? Does that always happen, or is that a new feature? I don't think I've ever heard that before. But fair warning. Happy Tuesday. Yeah, I think it's new too. I hope you're all doing well. I hope you had a good weekend. Welcome to class. So there is quite a bit to tackle today, and so I want to kind of jump right in. But at the very top, you should have received an email announcement from me that laid out a number of points, reminders, things to just keep in mind. You know, I really try on at least a weekly basis, and you'll see going forward, to, you know, send you a message just to kind of keep certain things in mind and to, you know, maybe prioritize certain ideas or things that should be on front burners and back burners and that kind of stuff. So I'll keep that up. And I just at the very top of class here want to know if there are any questions about that kind of more administrative email, or what was mentioned in there, what it is you need to be thinking about and doing, what resources I highlighted in that email for you in terms of the handouts. As you kind of think about that, because I do want to leave room for a few of those questions, I would just want to ask if there's anybody who is receiving that email at an email you would prefer it not go to. Please just put in like a chat message, private or public, which email it is that you would prefer. Because I get from the registrar a roster, and on that roster, it has a column called preferred email. And for most of you, it's just your AU student email. But for 3, 4, 5 of you, it's like a personal email address, Gmail or something like that. So I want to make sure I'm sending it to the right email, or the one that you would prefer it going to. And if it's going to a personal one and you want it sent to your AU email address, please just let me know that and I'll make the change. So going forward, it always goes where you want it to. With that said, what questions do you have, thoughts, ideas on the administrative front? Are there any questions in terms of the difference between practice problems and the problem set? Everybody understands that practice problems are purely voluntary. They're there for you to do if you want some additional practice outside of the starting with Stata tutorial or what we do in class. They come with a do file, which has my kind of walkthrough of the program code. So it's a bit of a cheat sheet, as it were, just to help you. I think the best way to tackle those practice problems is to try it yourself, right? Walk through the practice problem questions, try to answer them on your own. And if you get stuck, then consult my do file to see how I did it. So that would be my suggestion. Going forward, the practice problems will be a little bit less instructional, in the sense that in the first practice problems, I really said, click here, now type this. Going forward, the practice problems will still be more for teaching purposes, but they might be a little bit closer, maybe halfway closer to what a real problem set is, where I give you a question and you have to figure out how to go about answering it and producing the answer. There was a question here, reminding us when the problem set is due Saturday. Yes, the problem set is due Saturday at midnight. I wanted to give you a weekend day to work on it towards the tail end. I realize that we've been moving very quickly here at the beginning of the term, especially for those of you who, who had some issues getting Stata up and running in the first place, or just kind of making the transition into this very different structure of the class, and just kind of those preliminary getting going things. And so why don't we just say, after a couple of office hours consultations and things like that, why don't we say that having, at least for this first problem set, 2 full weekend days, we'll make it due Sunday night at 11:59. I'll include this in my, in my email. I don't want to constantly be moving the goalposts in terms of deadlines, but I really realize that we're two-timing it here, or double timing it, maybe is the better term. We're double timing it here in the summer semester, and so it has been a lot. I do realize in these first couple of weeks, and so. Just to give you a little bit of additional time to make sure you can work through those starting with Stata tutorials and feel comfortable entering into the problem set. Or as I discussed with a couple of people today, maybe feeling very uncomfortable moving into the problem set, but moving into it nonetheless, and having a little bit more time to work through it and to figure out what your questions and problems are, so that way you have more time to kind of deal with them and work through them once you've confronted them. We'll make it due Sunday, the 30th, Sunday, May 30th at 11:59 p.m. And we're going to have a Q&A period to talk about problem set 1 later in today's class session. That's going to be later on, though. We're not going to start class with that. And so any questions that you want to raise about problem set 1, I'm happy to address those at the time. Please don't make this kind of some sort of expectation that we're going to constantly push deadlines. That's just not something we can do assignment in and out, but here at the get-go, we can do that. So that'll give you an extra day. Good. So I know you all can read, and you did, and so I'm not going to kind of replay everything in that announcement, but I do want to emphasize just that little preface note at the top, because I think it's just important to calibrate our own expectations about workload during the summer. So as I mentioned there, right, during a normal semester, you go to class for 2.5 hours, and then you do about 5 hours of outside of class work for that class, right? And typically then you have like 3 of those. So, it fills up a good portion of your week. And I know you have internships or jobs or family issues or other things going on. I certainly respect and appreciate those things, but, being here is a fundamental priority, right? And doing the work that's required is a fundamental priority, just like having a job or just like, dealing with other things. So in the summer term, right, it's not 2.5 hours and 5 outside. It's 5 hours, right, of course content, and 10 outside. And so I just want to remind you that we're really, we should be devoting a solid 15 hours per week to this class. I tried to create the course in such a way that it matches that expectation. Perhaps at the get-go here, you might be investing a little bit more. I think as we start to hit our stride, I think you'll fall within that range much more easily, but please do keep that as an expectation. I think it would be very hard for you to succeed if you went with a typical academic schedule, like during the semester, of thinking you're going to, spend 5 hours outside of our class session and your asynchronous, lecture and reading. It's definitely just a class that requires your time, energy, and effort. And I know you're putting it in. And so I appreciate that at the get-go. Any other questions? Hey, I was wondering if someone could add. Okay, WhatsApp. Somebody did create a WhatsApp, I think, yes? Can someone speak to this? Go ahead, Drew.
I think it was, I'm usually in the Wednesday class. I think the Wednesday class has it. If I came to the Tuesday one, I thought it'd be the same, but.
So you know what you could do? What I would suggest is either you all for your kind of Tuesday evening course, feel free to create one. I mentioned this on day 1, feel free to create a WhatsApp. And so, but I'm not going to facilitate that because frankly, I'm not a part of it, right? So that's for you all to do. Or you just go to the discussion forum and say, hey, can you post the WhatsApp information that you all created in the Wednesday evening because us Tuesday evening folks want to join that? And that would be fine too.
I think I'll do that latter one. I'm gonna go post right now in the
Okay.
forum.
Yeah, I think that's great. I'm sure somebody out there has it. Okay. Anything else? All right. Well, with that said, we have a number of things. Let me just hit the class website here and remind myself of the order in which I wanted to go through some of this stuff this evening. Okay. Yeah. So you watched the video on hypothesis testing, right? The first one on statistical inference generally and univariate hypothesis tests. And then you transition to crosstabs, which is our first method to do a bivariate hypothesis test. In other words, to test the association or relationship between two variables. And as you know about cross-tabulation, right, that's when we have a categorical independent variable and a categorical dependent variable. And we're trying to test the extent to which those two variables are associated with each other. And we'll review that. And we'll also review univariate hypothesis testing. But in general, that shift that you made in the content for these two sessions, 4 and 5, are represent the transition from descriptive statistics, right, to inferential statistics. Descriptive meaning that we're generally just, as we talked about the first day of class actually, describing characteristics of our sample. What's the mean? What's the median? What's the standard deviation? Or if we have like a categorical variable, what's the frequency distribution? In other words, how many observations belong in each category and what percentage of them belong in each category, right? So we're just identifying some basic properties of a particular variable that measures something we're interested in. That's descriptive statistics we're describing, right? Inferential statistics is when we start to say something about a population, right, or a universe of cases based on a smaller sample drawn from that universe of cases. So that's the kind of leap we're making when we go from descriptive statistics to inferential statistics, right? We're trying to understand a broader population based on a sample drawn from that population. That's what brings us to this hypothesis testing approach, whether we're doing the univariate hypothesis testing, which we'll do an example of today, or whether we're doing bivariate hypothesis testing with an independent variable and a dependent variable, right? A potential cause and outcome, or two variables that we think are connected and associated with each other. In a univariate hypothesis test, right? Univariate meaning one variable, we're essentially taking one variable. I'm trying to remember what the example was I put in the lecture, but the example I'll give you in a few minutes is about levels of pollution. And we're trying to see if we have a pollution problem in general based on a sample of water or a sample of air to see what the level of pollution is within that sample. And based on that sample, we're trying to make an inference or draw a conclusion about whether the entire body of water or our entire atmosphere has a pollution problem. And we do this in all sorts of different ways, right? And I want to show you a little bit of a video here at the outset through PBS by Nova that I think captures some of this approach to hypothesis testing and statistical inference really well, and in kind of American politics terms to some extent that I think resonate with a lot of people. And so right at the outset, we're just going to watch this video, and please, jot down notes and be prepared to make some observations, ask some questions, or have a discussion about it. So with that, let me share my screen here. And my sound. And I want to jump to
so as you step ahead, different forecast
right here.
Experience as gravity. In fact, the scientific method demands a hypothesis which leads to a prediction of results from a carefully designed experiment that will test its claim. Surprisingly, it wasn't until the 1920s and 30s that a British scientist, Ronald A. Fisher, laid out guidelines for designing experiments, using statistics and probability as a way of judging results. As an example, he told the story of a lady who claimed to taste the difference between milk poured into her tea and tea poured into her milk. Fisher considered ways to test that. What if he presented her with just one cup to identify?
If she got it right one time, you'd probably, well, yeah, but she had a 50-50 chance just by guessing of getting it right. So you'd be pretty unconvinced that she has a skill.
Fisher proposed that a reasonable test of her ability would be 8 cups, 4 with milk into tea, 4 with tea into milk, each presented randomly. The lady then had to separate them back into the 2 groups. Why 8? Because that produced 70 possible combinations of the cups, but only 1 with them separated correctly. If she got it right, that wouldn't prove she had a special ability. But Fisher could conclude, if she was just guessing, it was an extremely unlikely result, a probability of just 1.4%. Thanks mainly to Fisher, that idea became enshrined in experimental science as the p-value, p for probability. If you assume your results were just due to chance, that what you were testing had no effect, what's the probability you would see those results or something even more rare?
If you assume that there's a process that is completely random and you find that it's pretty unlikely to get your data, then you might be suspicious that something is happening. You might conclude, in fact, that it's not a random process, that this is interesting to look at what else might be going on, and it passes some kind of sniff test.
Fisher also suggested a benchmark. Only experimental results where the p-value was under 0.05, a probability of less than 5%, were worth a second look. In other words, if you assume your results were just due to chance, you'd see them less than 1 time out of 20. Not very likely. He called those results statistically significant.
Statistically significant. Now, this is a terrible word. It could be quite insignificant. You could be detecting a very, very, very small effect, but it would be called, in the mathematical lingo, significant.
Since Fisher's day, p-values have been used as a convenient yardstick for success by many, including most scientific journals. Since they prefer to publish successes, and getting published is critical to career advancement, the temptation to massage and manipulate experimental data into a good p-value is enormous. There's even a name for it: p-hacking.
P-hacking is when researchers consciously or unconsciously guide their data analysis to get the results that they want. And since 0.05 is kind of the bar for being able to publish and call something real and get all your grant money, it's usually guiding the results so that you arrive at that P of 0.05.
How much p-hacking really goes on is hard to know. What may be more important is to remember what was originally intended by a p-value.
The p-value was always meant to be a detective, not a judge. If you do an experiment and find a result that is statistically significant, that is telling you that is an interesting place to look and research and understand further what's going on. Not, don't study this anymore because the matter is settled.
In a sense, a low p-value is an invitation to reproduce the experiment, to help validate the result. But that doesn't always happen. In fact, there are few career incentives for it. Journals and funders prefer novel research. There is no Nobel Prize for replication. Another solution to p-hacking and the overemphasis on p-values may simply be greater transparency.
More and more, what people are doing is publishing their data. And so it's becoming harder and harder to lie with statistics because people will just probe and say, well, give me the set you analyzed and let me see how you got this result.
Statistics continues to play a fundamental role in science, but really anywhere data is collected, you'll find statisticians are at work, looking for patterns, drawing conclusions, and often making predictions, though they don't always work out. The presidential election of 2016 was a tough one for pollsters, the folks who conduct and analyze opinion polls. Hillary Clinton was the overwhelming favorite to beat Donald Trump right up to Election Day.
Trump is headed for
Let's pause there. We'll come back and watch a little bit more in a few minutes, but let's make a few observations about what you've seen and learned so far from this video. Statistical significance, p-values, probabilities, randomization. I mean, there's a number of things that came up there. What did you observe? Oh yeah, Joseph.
This isn't so much an observation, but as a question of the p-value. I've gone like back and forth in my mind of understanding what the p-value is, but in that video, it said a low p-value is an invitation to review your results. So am I right in thinking that a low p-value rejects the null hypothesis, and then you would review the alternative hypothesis? Is that what it meant?
Yeah, I think that's right. And it's not just that you would review the alternative hypothesis, or what's sometimes called the research hypothesis, but it's that you would conditionally accept it. And now, you know, there are debates about that, but I'm willing to say that when you reject the null hypothesis, it doesn't mean that we full stop with any certainty accept the alternative hypothesis or the research hypothesis, but it means that conditional on the data we have from the sample we've collected with the tests that we've run, there is sufficient evidence to say that there is an association between these two variables, well, I'll leave the univariate stuff for a few minutes from now, but that there is evidence that leans in the direction of our alternative hypothesis to the extent that that evidence meets a threshold that we've set to feel confident about it, right? I mean, that threshold that Fisher said or suggested was 0.05. There are a lot of folks these days who think, given the amount of data we have, we should revise that standard to something much less than 0.05. So that way it's kind of a more stringent standard to obtain statistical significance. You have folks, you know, who kind of follow a more Bayesian logic. I don't know if any of you have heard about Bayes' theorem and a Bayesian approach to statistical inference, but they have argued more than any other, I think, that we should reduce the p-value that we consider our standard in social science from 0.05 to something much smaller, 0.01 or even 0.001 or something like that. And that's simply because I'm getting a little bit ahead of your question here, but that's because generally speaking, our p-values from our actual tests get smaller and smaller and smaller when the number of observations we have in our study or in our sample are greater and greater and greater. And we'll see this mathematically, and actually I guess you did see it mathematically a bit already in the lectures, where as n increases, that's generally in the denominator of the equation, right? And as the denominator gets bigger and bigger and bigger, the actual value is going to get smaller and smaller. And so long story short, I think you put it pretty well, and that is a p-value below what we set as our critical threshold, which is generally 0.05 as a baseline standard. A p-value below that means that we reject the null hypothesis in favor of the alternative hypothesis, right, or research hypothesis, to suggest that our evidence at a sufficient level of confidence points in the direction of the alternative hypothesis, right? We can reject the idea with a large degree of confidence that we're observing these results due to random chance. And that was the point about the teapots and all of that, right? She had a 1 in, I can't remember the exact value, but she had a 1 in something chance of guessing correctly or answering correctly the milk into tea versus tea into milk, right? But it was a 1 in, I can't remember what the exact ratio was, but it was a 1 in, 864 or something like that chance. Or maybe it was something much less than that. Maybe it was 70 something. Or yeah, I guess it would be 4 and 4 is 3 times 2 times 1. Yeah, it's in the 70s. And so, yeah, exactly. And so yes, you can still get that answer by chance alone. The question is, what is the probability of getting those results purely by chance? And if it's a very small probability, then it's a very low p-value. And we can reject the null hypothesis under those conditions. Giselle, go ahead.
I was wondering if there is any kind of way to know what is the smaller amount of variables in the sample, or what is the smallest sample that we can have to make our test valid if we have a limitation on resources and all of that. I know that he just said okay, maybe 8 cups of tea would give me 70. So it was 1 in a 70 chance that she gets it right. But is there a formula for actually having something structured?
There is, and so there's something called statistical power, and there is an equation and different ways to determine the statistical power of your test. I didn't include that in the lectures for you all, and I generally don't even teach it during our class because I don't want people, I don't want students trying to meet that standard because it's such a minimal standard that I think we want to aim for something much bigger. So generally I talk about having a sample size that's hundreds, thousands, tens of thousands, hundreds of thousands of observations, right? Such that generally speaking, the more data, as long as it's collected in a sound manner, right? And systematically, the more data, the better. And so yes, there's an equation for statistical power, and we can talk through that another time if you'd like. Maybe in office hours or the discussion forum would be a good place where if you ask the question, I can respond there more. But generally speaking, I mean, and at the end of the day, it depends on what p-values you want to allow for, right? What that threshold is that you require. If it's a p-value of 0.1, then it's below 100. But generally that doesn't quite, as she said, pass the sniff test for a lot of social science research, where we want to see p-values far less than that before we're willing to reject the null hypothesis. right? And so, yeah, that's the short answer. What else? There was a little bit of commentary in there about p-values and p-hacking or some of those things. Nicole, is this on that line or something else?
A little bit.
Go ahead.
So I was thinking about not only the p-hacking part, but just the data collection part. Like they were talking about replicating a lot of the findings for the data. But then, I just want to point out also, you want to go to the source and see how we're replicating the data collection part too.
Yeah, absolutely. And to pick up on, kind of connect that with Joseph's point from before, about rejecting the null hypothesis and whether that means we should then review the alternative hypothesis. Generally, if we do reject the null hypothesis and therefore have statistical significance, meaning we have sufficient evidence to support our alternative hypothesis, that we would conditionally accept it, that I said before. This is where we would generally want to have additional studies go about replicating or reproducing the same study, but with a different sample, right? Because ultimately we might have gotten a statistically significant result from this sample, but we should probably go back and resample and see if we get similar results. And then we should probably go back and resample again and see if we get similar results, right? Because one test or one study does not a scientific finding make. And that's something that I think was a message in the Easterly reading that we did on day one, actually, right? It was this notion that we shouldn't necessarily create policy because one study says that, foreign aid placed in places that have good governance will produce economic growth in a way that it won't in other places, right? Now, maybe that is the case, but we shouldn't hinge all of our policy decisions or our understandings of what's truth, or what's true versus false based on a single study of anything or some claim of statistical significance from one study that comes from one sample and one set of tests, right? Instead, a statistically significant result should be an invitation more than anything else. Right? It should be an invitation for other people to try to replicate our findings or reproduce them with their own study. And additional studies will differ in a number of ways. The main way that I just mentioned might be with drawing a new sample, right? But another way would be to measure our variables slightly differently, right? So in study number one, it came from this sample and they measured their independent and dependent variables in this way. Study number two might draw a new sample and they also might think that an alternative operationalization of the same concepts, right, of the same variables would also be a way to kind of check that original study to see if the results hold, not only with a new sample, but with an alternative way of measuring the variables in that first study, right? Using kind of a different instrument. And there are a number of other ways, right, that studies can try to replicate or somewhat reproduce an original study, but make some changes aside from the sample to see if the results hold up under different conditions. And if, let's say, 9 out of 10 future studies based on a first one trying to replicate and reproduce its results point in the direction of that first one's results, then all of those combined in aggregate represent more and more evidence that support that original study, right? But sometimes a replication or reproduction of that original study or a new iteration of that same general study and hypothesis will point in a different direction. In which case we say, oh, well, we're less confident about the results from that original study, even though it had statistically significant results. We now have another study that doesn't have statistically significant results, right? And where our findings point in the direction of the null hypothesis instead of the research hypothesis. And so in general, we want to, this is what's so important about reviewing the literature in general, right? Again, a single study does not a fact make. We really need to kind of take many studies that are all dealing with the same research question and the same hypothesis and take them in aggregate to see how strong the evidence supports one finding or another, right? You take something like climate change and it's a no-brainer because 99.5% of the studies, kind of point to certain, certain general findings, right? That climate change is happening, number one, that there's an anthropogenic element to it, number two, right? That it entails some amount of temperature warming, number three, that it's partly responsible or partly due to, thinning of the ozone layer, number four. And all of these things after study after study after study are reinforced. And you might have one study out of 100 or out of 200 that points in an alternative direction, right? But when 99 out of 100 point in this direction, then we can say there's some sort of scientific consensus, in that direction. But there are a lot of other research questions out there and hypotheses that don't have that kind of overwhelming support. And that's where more studies are necessary, right? To kind of figure out where the debate lands or how much evidence we have for this side of the debate versus that side of the debate. Okay, so that was excessive, but nonetheless. What other questions or observations do you have from that first part? Right, you saw that in the line of research, there is some incentives that point toward doing what they call p-hacking, which is kind of manipulating your approach to statistical analysis or the sample you draw or other things to try to obtain a p-value that meets that 0.05 kind of baseline. It's the one that in a regression table in a study, right, in a research paper, allows you to put those little stars to say that your independent variable is statistically significant for explaining the outcome. And so there are kind of adverse incentives. And I think one of the comments in there pointed to the fact that more and more, because of the requirements of sharing data and computer power that allow us to reproduce and replicate each other's studies, there's perhaps less and less of that kind of manipulation happening. And the incentive is towards really kind of clean and coherent quantitative analysis. All right, so now let's get a little bit more into the notion of inference. And this will just be another 10 minutes or so, and that'll wrap the film.
Or a historic defeat. He's going to lose by a landslide.
I think that she's going to have a very good night.
The New York Times put Trump's chances at 15%. One pollster on election night gave him 1%.
A projection of a 99% chance of winning, is that correct?
The odds are overwhelming of a Hillary Clinton victory on Tuesday. I would be very surprised if anything else happened.
And of course, Trump won, and Clinton lost.
People were repeatedly told Hillary Clinton is the candidate most likely to win this election, and she didn't. And I think that really left people feeling almost lied to, almost cheated by these numbers.
So what was going on with the polls? And exactly how do people predict elections? One way is just by asking people who they'll vote for.
One of the great things about polling is that we don't have to talk to everybody in order to find out what the opinions are of everybody. We can actually select something called a sample.
Sampling is a familiar idea. To see if the soup is right, you taste a teaspoon, not the whole pot. To test your blood at the doctor, they typically draw less than an ounce. They don't drain you dry. But in many circumstances, finding a representative sample is harder than it sounds.
Let's suppose that this is the population of about 1,000 people in a city. And we want to know, are people for or against converting a park into a dog park? And so these green beads down here are going to represent people who are for it, and the red beads are folks who are against it.
Talithia's first step is to take advantage of an unlikely ally in sampling: randomness.
The beauty of randomization is that as long as you throw everything from your population into one pot and randomly pull it out, you can be sure that you're within a certain percentage points of the actual value that's in that pot.
So the plan is to randomly sample the beads. But how many? That depends on how much accuracy Talithia wants. One measure is the margin of error, the maximum amount the result from the sample can be expected to differ from that of the whole population. It's the plus or minus figure, often a percentage, you see in the fine print in polls. But there's also confidence level. Inherently, there is uncertainty that any sample really represents a whole population. The confidence level tells you how sure you can be about your result. A 90% confidence level means, on average, if you ran your poll or sample 100 times, 90 of those times it would be accurate, within the margin of error. Talithia knows the total number of beads is 1,000, and she's settled on a plus or minus 5% margin of error at a 90% confidence level. That means she needs a sample size of at least 214 beads.
Real quick, I just want to say that this is I forgot this was even in this video. This is the question Giselle was asking before. What they just ran there is statistical power, right? I mean, these are the components of statistical power to figure out what sample size is necessary, right? To have sufficient statistical power to run this hypothesis test, right? So you set a kind of desired confidence level and margin of error and the underlying population and the size of the underlying population, and it will tell you what sample size is necessary from it, right, to draw from it. I can, if you put this in the discussion forum later, I can actually drill it down for you, but that's essentially what they just ran through there.
We got 103 red beads and 111 green. So about 48% of our population would vote against and about 52% would vote for. Now, remember that margin of error that we talked about, that plus or minus 5%? So once you take that into account, those numbers really aren't that different at all. So I guess you could say this puppy is too close to call.
In fact, within the margin of error, the stats got it right. There were an equal number of red and green beads in the jar. While the sampling error built in from the mathematics can be quantified, there are other errors that can't.
The other parts of the error, how we word our questions, how the respondents feel that day, the responsibility to predict what their behavior is going to be somewhere down the line. All those sources of error are something that we can't calculate.
And there's a catch to random sampling for polls, too. A few decades back, when just about every household had a landline, finding a random sample meant randomly dialing phone numbers.
Into the 1970s and the 1980s, we were getting 90% response rates. If we randomly chose a phone number, somebody on the other end of that phone would pick it up and would do the interview with us.
Those days are over. Thanks to caller ID and answering machines, people often don't answer their landlines anymore, if they even have one. Response rates are way down.
Only about 10% of people respond to polls, so you're kind of crossing your fingers and hoping the people you reach are the same as the ones that are actually going to vote. For example, we found in 2016, pollsters were not reaching enough white voters without college degrees.
If there's a bias in the data, you cannot recover from it, as we've seen from some recent elections.
After Donald Trump's surprise win, many wondered if polling was broken. But if you look at the polls themselves and not the headlines, on average, polls on the national and state level were off by historically typical amounts.
So when I hear people say, oh, the polls were wrong, then it partly reflects people's interpretations about the polls being wrong, where people, for various reasons, looked at the polls and they said, these numbers prove to me that Clinton's going to win. When we looked at the polls, we said, these numbers certainly make her a favorite, but they point toward an election that's fairly close and quite uncertain, actually.
And in 2016, the US presidential election was just that close. Trump's victory depended on fewer votes than the seating capacity of some college football stadiums, spread across 3 states: Pennsylvania, Wisconsin, and Michigan. And there were some problems with the polls in those states that led to underestimating Trump's support, according to a postmortem by a consortium of pollsters. Nate Silver, the founder of the website 538, is one of the biggest names in polling, even though he doesn't generally conduct polls.
Our job is to take other people's polls and to translate that in terms of a probability, to say basically whether who's ahead, which is usually pretty easy to tell, but then how certain or uncertain is the election is the more difficult part.
Like a meteorologist, Nate presents his predictions as probabilities. On the morning of Election Day 2016, he gave Clinton about a 70% chance of winning and Trump about a 30% chance. That's like rolling a 10-sided die with 7 sides that are Clinton and 3 that are Trump.
People who make probabilistic forecasts, they're not saying that politics is intrinsically random. They're saying that we have imperfect knowledge of it, and that if you think you can be more certain than that, you're probably fooling yourself based on how accurate polls and other types of political data are.
Ultimately, interpreting a probability depends on the situation. While a 30% chance might seem slim, if you learned the flight you were about to board crashed 3 out of every 10 trips, would you get on the plane?
As this plane only makes it to its destination 7 out of 10 times, please pay attention to our short safety briefing.
Or if a weather forecaster said there's only a 30% chance of rain, and then it rained, would you care?
If it does rain, no one demands to know, why did it rain? We have to get to the bottom of this. We can say, like, it just did. It might have rained, it might not have rained, and as it happened, it did. I do think there's a certain natural resistance to seeing things that maybe we care about more than whether it's going to rain or not, like elections, in that same way.
Okay, so, you know, a lot to chew on there, and I might just invite you, kind of for the sake of time, because there's a lot that I want to get through, you know, to reflect on that a bit, to take it to the forum if you'd like, and to watch more. I just posted for you a YouTube link to the whole video. That's recent, actually. I don't believe that that YouTube video was available, at least not when I first started showing it to this class. I had to, you know, go onto PBS and kind of share my screen there. And then I just realized recently that it's actually on YouTube. So feel free to go and watch more about it. It contains some other very interesting things about quantitative analysis and statistical analysis in general. But I think, you know, some of the key takeaways from all of that is, you know, would be that, you know, statistics predicts the likelihood of future occurrences based on real observations that we have, right? Real empirical data. And it depends on the mathematics of probability. And, you know, if we were in a more advanced class of people who really wanted to go into statistical research for certain across the board, we might have, you know, spend some more time on the math underlying probability theory, but I'll spare you all that this semester. But at the end of the day, right, probability, as you read about in the Whelan reading, is the study of events and outcomes that involve some element of uncertainty. And to some extent, that's what we're really trying to do with statistics is measure the uncertainty around our predictions, right? Our predictions or explanations of variation in outcomes are based on potential causes that we put forward as hypotheses, right? That this cause affects this outcome, or variation in this X produces variation in this Y. And we can determine the level of association between those two things and make some judgment about the extent to which X and Y move together in a systematic fashion. But no matter what, unless we were studying something like, physics or chemistry, and even there's some error, right? But especially in the social sciences, where we're talking about a very complex world, there's going to be some degree of uncertainty and error. And we're trying to kind of measure that to see if that uncertainty around our predictions or uncertainty around our explanations is small enough to reject the null hypothesis that these two things are not systematically related in terms of the alternative hypothesis that they are. And so again, I think one of the takeaways from that film is that probabilities don't tell us what's going to happen for sure. They tell us what is likely to happen, and what is less likely to happen. And we're trying to capture that kind of margin of error, that likelihood, that error band around our explanations and predictions. And so we're going to see that come up more and more and more as we work through the different methods that you're going to learn. So far you've done univariate hypothesis tests and cross-tabulation as your first bivariate hypothesis test. And we're going to put those into practice, and we're going to add to them quite a bit as we go forward. Good. Any final comments before we move on to the next part of class? Okay. So with that said, let's take a few minutes to review. No, let's not do that. Let's work right into a practice problem. So on the class website under handout 6 is univariate hypothesis test example. I want you to go and download that onto your computer and open it, please. And in terms of Tyler's question, just while you're doing that, he asks, is the null hypothesis always that there is no, she asks, excuse me, is the null hypothesis always that there is no statistical relationship? Not exactly. The null hypothesis states that there is not the relationship that your alternative hypothesis asserts. And that's why it's a nullification of your alternative hypothesis. What's the difference between the two? Your alternative hypothesis has to state a connection between two variables as well as a direction of the connection. So let me take a super generic one. I think I used this with you once before, but that an increase in democracy, let's do it this way. An increase in national wealth increases the likelihood of democracy, right? So notice that I've attached a cause and an effect, right? Economic wealth and democracy, but I've also said what the direction of that relationship is. It's a positive relationship, that when national wealth increases, democracy also increases, right? And so the null hypothesis would say, no, it doesn't. Right? It doesn't say that there's no relationship between them at all. It says that when national wealth increases, democracy does not increase. Are you? Okay, I'll take care of the handout. Hold tight if you're having trouble opening it. But just to Tyler's point, I think that's an important question in terms of how we phrase, but then also how we think about the null hypothesis. right? It's simply a nullification of your alternative hypothesis where you insert something like is not or does not into your alternative hypothesis statement. So when national wealth increases, democracy also increases becomes when national wealth increases, democracy does not increase. But it doesn't make a commitment in terms of whether it decreases, perhaps, right? Okay, very good. I don't know what's up with the handout. Hold tight 1 second. Let me see what I can do here. Weird. Okay. Let's do this. Break. So now what I would like you to do, please, is refresh the class website. Just refresh your browser. Scroll back down and go ahead and click it now. And you should be able to open it up. Okay, and so what I want you to do is take the next 10 to 15 minutes, okay, and work together in groups on conducting this univariate hypothesis test based on this scenario. Okay, I'm going to put you in just like 2 or 3 rather large groups, just so you can have more, brain power in each space. And let's just kind of talk through a couple of things really quickly, though, before I send you in there. Number one, read the scenario. A random sample collected 300 readings of the level of a pollutant in the air across a country and found an average level of 1,271 parts per billion of that pollutant with a standard deviation of 150 parts per billion in that sample. Right? So across those 300 readings, which represents the sample we drew, the average, the mean level of pollutant is 1,271 parts per billion. And the standard deviation, which represents the spread or the variance around that mean of 1271, is 150 parts per billion. Right? So remember that the standard deviation is telling you the kind of average difference between the mean itself and all of the 300 observations that make up that mean. You follow me, right? That's just back to kind of the basic interpretation of standard deviation. So that's the answer, because I worded this kind of oddly and I should have changed the wording, but that's the answer to question A. All right, so you already know A. A is just 1271 and 150. So then you can go ahead and move right to B, where you need to calculate the standard error. Calculating the standard error comes from a previous class, right? And it should be in your notes about how you calculate the standard error, so you can go about doing that. Okay, so I'm going to put you in 3 breakout rooms, and you can go ahead and start in B. And if you want to, apparently there's a way that you can summon my attention when you're in a breakout room. I just learned this last semester. So feel free to do that if you need me to hop in. All right, go ahead.
for some reason.
Oh my gosh.
Yeah, that's what it did for me originally, but I've got it. Hold on.
Thank you. Thank you.
Yeah.
So you all are on part B, yes?
Yes.
Okay. Did you already calculate the standard error? All right. How do you go about calculating the standard error?
It's the standard deviation divided by the square root of the sample population, right?
Perfect. So we know that, and again, maybe this is just confusing language, but the estimated mean is 1271, right? So it's still the same as in part A, that the estimated mean, right, is still 1271. And the standard error, as you said, is going to be 150, because that's the standard deviation, divided by the square root of our sample size, which is 300. So 150 divided by 17.32, right, gives you what? Anybody? 150 divided by 17.32?
Is it 8.66?
Okay, 8.66. So now you have your standard error. So, put a pin in that. Now you can move on to C. C is how we obtain the z-score, right? The z-score is the number of standard errors between our hypothesized value and our observed mean. Our observed mean, again, is our estimated mean, 1271, right? Our hypothesis is what? What's our hypothesized value, you think, based on the scenario that I described there in part C?
50.
Say that again?
Would it be 1250?
Exactly, it's 1250 because that's kind of the standard, the reference point. It's what we're wanting to judge our sample mean against. So we have a sample mean of 1271, but remember that sample mean is composed of 300 observations, some of which are probably below 1250, some of which are probably, well, certainly above 1250, right? And there's 150, a dispersion value, a standard deviation of 150 parts per billion, that kind of spreads out our estimate of pollution. And so we want to essentially judge our 1271 mean against our 1250 standard, taking into account that 8.66 standard error. And so if you look back to the equation for the z-score, it's the observed mean minus our expected or hypothesized mean. So 1271 minus 1250 divided by the standard error, which, as we just heard a second ago from Mustafa, was 8.66. So go ahead and do that calculation out. And then once you do that calculation, I want you to try to just do a basic interpretation of your results, right? You're going to get a z-score, and then you can look up that z-score and see what its associated p-value is. And you can just do that with a z-score table, right? If you want to Google that, it was also in the lecture. I think I provided a link in the PDF, but you can just look up z-score table and go and see if you can figure out what the z-score is that is the p-value is that is associated with your z-score. Okay. Once you've done that work in the next 2 or 3, 4 minutes, go ahead and just open up a link next to where you got this handout called solution, and that'll give you the answer. Okay, and go ahead and just read that over and discuss it amongst yourselves, and I'm going to hop over to another group.
Professor, just a quick question: is the z-score the same link that you added on the document here? It says, like, for example, in section C, it says a z-table can be found here. Is that the very same z-score that you were talking about?
Yes.
All right, thank you.
Yes. Oh yeah, I forgot I put a link in it. Exactly. Exactly. You're welcome.
Have a
Hey, he's here. You can ask.
all right. Back.
That's such a rude entry there. Sorry about that. So where are we?
We're on C.
Okay.
We had a dispute, and we were hoping we could ask you.
Good.
Z equals, and then it's 1271 minus 1250 over, and then are we doing standard deviation or standard error in this instance?
Standard error.
Yeah.
Okay.
So would it ends up being 2.42?
Correct. I know that you might find it other ways, online or in certain class or what have you, where you don't dividing by standard deviation. But no, we'll do the z-score with standard error.
Okay, cool. Well, thank you, Dr. Spath.
Absolutely. And so, yes, Tyler's 2.42. And so then you can go ahead and use that table, the Z table, which is in the prompt, and find the associated p-value. Kind of think about the interpretation of that. And then once you're done, go ahead with, identifying the associated p-value and interpreting it with one another. On the class website where you got that handout 6, there's now also a link called solution, and you can open that and read mine. And I'm going to hop on to another group.
Thank you. Thank you.
Model and tells you how far to the right or left you would like move the kind of like bar probability. So if you used either, if you just looked at a z-score table and looked up to like 2.42, it would be something like 98 or 99 whatever. So you'd have to do 1 minus that. Or if you look at a negative z-score table, it'll just tell you what your p is.
Gotcha. Thank you.
You got it?
Yeah.
I know it's kind of weird. The Z, like looking at the table can be kind of weird because if you have a big z-score and you're just looking at the positive tables, you'll get like a big p-value and you'll be like, wait, like this is wrong, but it's not.
Thank you.
That's a good explanation. I came in at the tail end, but that was good, Max.
Oh,
so it looks like you already got through C, right? Because you were mentioning 2.42. So you obviously got the correct z-score. And then you already found the associated p-value with that. Okay, and you went about interpreting the p-value already for parts D and E, or especially E, or no?
Yeah, kind of. I mean, I think it's safe to reject the null hypothesis that the error is safe.
Yes. So what I would like you to do, so if you all discuss that and you're all the way through, it sounds like the problem. Next to the handout 6, there's also a link for solution, and that just has me walking through that that problem that you just walked through, so you can kind of check your work against mine, and also check your kind of final interpretation with mine in part E there. And then we'll come back in just a minute and we can have any final discussion and then move on to the next thing. Okay. All right. I'm gonna have to figure out how to turn that off. That's terrible. Okay, welcome back. So it seemed like all three groups made their way through that example problem pretty efficiently. What questions do you have about that? I mean, is it pretty clear in terms of how you went from a real world scenario with a sample mean, and a sample standard deviation, and worked through to do a hypothesis test to make some sort of judgment about whether the air in general has a pollution level above the recommended standard, right? And how confident you could be in making that assessment. Do you understand how you walked through that? What questions do you have, Neville?
I'm still kind of confused on how we get from our z-score to our p-value.
Sure. So essentially, you hop to that table, and that table is this, let's just say, special representation of that link where it takes the outcome of that z equation, right, which is your z-score of 2.42, and translates it into a probability value. And I'm just looking for a pen here real quick, so I might be able to draw this up just very efficiently, hopefully. Let me see if I can do this. This is from last class. Okay. Andrew, go ahead while I'm pulling this up.
We kind of hit a roadblock in like the last 30 seconds there. I think there were a lot of people in the group that were kind of on two different ends of the spectrum here. We were wondering whether we are going to go negative with the Z or positive, but I was wondering if you were to use the negative value, you could say, okay, that 0.78%, you have a 0.78% chance that the air is safe. Or on the other hand, you could use the positive version to demonstrate that's the percentage in which the air is dangerous, correct?
That's correct. And I understand why that's confusing. And I think in a future example, I won't do a one-tailed test or a Z, essentially a test that looks only at one direction. So the kind of trick to that and the difference between a one-tailed test and a two-tailed test comes down to whether we can rule out a hypothesis that looks in one direction or the other, right? In a positive direction or a negative direction. And so in our example, I'm just pulling this back up again so I have it in front of me. What we're doing here is an upper tailed test, right? Because what we want to know is our observed value of 1271 above a particular standard or threshold, right? We're judging our estimate against a standard that we don't want to cross in the positive direction, but we're more than happy for it to be incredibly low. It can run all the way to 0 and we're fine, right? So as long as the pollution level is less than the 1250 threshold, then we're okay. So our hypothesis test is about whether it is over that and whether it is over that in a systematic way. I mean, obviously our sample mean is above, right? It's 1271. But that sample mean is composed of two things that we need to consider. One is it's composed of 300 observations, some of which are below 1271 and some of which are above 1271, right? That's why we have a mean of 1271, right? We have some observations above it, some observations below it, and maybe lots of those observations are below 1250, right? In which case, all of those samples would suggest that the air is safe. So that's one thing we have to consider, right? The possibility that we have many observations that are below the 1250 mark. The other thing we have to consider is that we have, as a corollary to that, variability, variance. And that's captured by our standard deviation. How much variance? Well, 150 parts per billion is our standard deviation. And so we have to consider that variance when we're trying to judge whether our 1271 estimated mean or sample mean should give us so much pause that we say with confidence that the air is unsafe, right? Or whether it's possible that we got a sample mean of 1271, but we can't rule out the possibility, right, that that's due to chance or due to error, and we don't have enough evidence to really say that the air is, unsafe at the level of confidence that we require, right? And you think from a policy or practical perspective, especially if this means that we're going to have to invest tons and tons of money or resources or things in trying to reduce, the air pollution or increase the air quality, right? Maybe we don't want to do all of that if there's a good chance that that 1271 sample mean is, due to chance or has a significant likelihood of not actually being systematically above 1250, right? If we can't rule out the possibility with a great degree of confidence that that's due to sampling these 300 air tests and not something more just kind of systematic in terms of air pollution. So all in all, I think those are the two ways to deal with that, right? One is when you have this upper tail test, where our hypothesis is that our observed value is greater than some hypothesized value, then we would do 1 minus the p-value we obtain, right? Or you can simply look at the other side of the z-score table, which I think is what I did in the example. I'm trying to remember, but I think I just, you get a z-score of 2.42, and since they're directly inverse, right, the p-values, I'm looking at my solution sheet right now, and you see that I just looked at the negative 2.42 instead of 2.42, right? I looked at the z-score equals negative 2.42, so I don't have to do 1 minus the p-value, right? I didn't have to do 1 minus 0.99, what would that be, 22? Go ahead, Andrew.
Yeah. I think what we were doing there was just kind of confused about how we portray the results, I guess. I think that for a while there we were kind of confused about, well, do we use the negative side of but I think that you could use both, correct? Because then you're just reporting whether it's clean or whether it's dirty, basically.
Correct.
Okay.
Yeah, it's like two sides of the same coin, right? Exactly. So then to the previous question from Neville, right, just here's the point, and let me make this into a broader point that will help set the stage for what we're coming to in the class over the subsequent weeks, right? So number one is that we have this z-score, right? And that z-score is an equation, and the equation, as you know, is the observed value of the mean, what we call the estimated mean, minus the population mean. But remember, we don't know the population mean. We don't know it. We're estimating it. That's the whole point of taking the samples in the first place, is to try to get a good guess, of what it is. And so instead of putting the true population mean in there, right, we're putting some standard value or some reference point against which we're trying to judge our sample mean. And so this is the one we observe, 1272, and this is the one that we're judging it against. some hypothesized value. In this case, the hypothesized value is a value we don't want to surpass. And so that's why we're making it our hypothesis. Is 1272 statistically significantly greater than 1250 in our sample? What we also want to consider about our sample are a couple of key characteristics. One of them, and both of them are contained in the standard error, right? One of them is the standard deviation. I mentioned that a minute ago because that's a measure of variance, right? The standard deviation is a measure of the spread in our data around the sample mean. The other thing that we want to take into consideration is our sample size. And so notice here that the standard error, right, takes into consideration both the variance in our data around the mean as well as our sample size. And that's why we use the standard error in the denominator. Now, in some z-score tests, you see they only use the standard deviation, but I use the standard error as well as lots and lots of others, right? Because it also incorporates our sample size very nicely. Okay. Now, what we want to know is, does the z-score, let me see if I can draw this really quickly. I mean, this is also in that table that you saw, but let me just see if I can try to do this fast. Oh, wow. Okay. All right. Wow, this is just really hard to do. Okay, that's better. Pretend that this is that this is a normal distribution. Okay. The question is, where is our z, right? Where is z along this spectrum, right? This spectrum has our standard errors in it, right? And so we might think this is, you know, this might be our mean value here in the middle, right? And we're wondering, where is our standard, where is our z-score when we go out standard errors, right? So this is -1 standard error. This is +1 standard error. This is +2. This is -2. Okay. And what we know is that, and again, we're talking about these standard errors. And what we know is that, let me see if I can zoom in a little bit here, is that once we get, you know, 2 standard errors away from the mean value, so here and here in either direction, so we're moving to the extremes, right? And once we move 2 standard errors in either direction, how much probability space, right? Because all of this under the blue curve is a probability, right? That totals up to 1. So this entire probability space underneath this curve here, right, equals 1. And so what I want to know is how much probability space is left in this tail and how much probability space is left in this tail, right? Well, we know from the 68, 95, 99 rule that you read about, right, which comes a bit from the central limit theorem and other things, is that the probability space, once we're 2 standard errors from the mean below this curve, is 0.025 and 0.025. Now, when you add up 0.025 and 0.025, what do you get? 0.05, right? And so now this probability space here in purple and this probability space here in purple, when you add them up, right? So the probability space that's in purple equals 0.05. So what we want to know, and this is if we were doing a 2-tailed test, and I'll shift gears on this in just a second, but this is if our hypothesis doesn't commit to being only greater than a certain threshold, like we did, are we above 1250? This is if we're, you know, above or below a certain distance from the true population mean. And so what we want to know here is, does the z-score push high enough to enter into this space, Or does it push low enough, right, to enter into this space? And so if our p-value is greater than, if our z-score is greater than a certain number in the positive or negative direction, then it's going to be associated with a probability space, a p-value below 0.025 on one of these two tails, right? And so again, our z-score, which as we said before, is a function of the difference between our estimated mean and some hypothesized value, like 1250, divided by the standard error, right? So it comes from characteristics of our sample, as well as some hypothesized value, like 1250. Our z-score is going to have to be placed on this line that is associated with a certain amount of probability space in the tails. That probability space to the left or right of the z-score, let's say it's here, right, is our p-value. A p-value below 0.05, right, means that we should reject the null hypothesis. A p-value above 0.05 means that we don't have enough evidence to reject the null hypothesis. And again, what does this have to do with evidence? Well, the z-score comes from evidence, right? The z-score comes from characteristics of our sample, 1272 parts per billion in pollution, 150 parts per billion as our standard deviation, 300 samples drawn. And so again, our z-score is not just some, some fictional number. It is derived directly from what it is that we collected from the world around us, right? The data that we observed and collected empirically. That, though, gets processed through an equation that ultimately tells us how confident we should be in rejecting the null hypothesis. And do we meet a certain level of evidentiary criteria in order to reject the null hypothesis or not? And that's really kind of what we're after here. And so that's just to go back to Neville's question, I mean, that's the link between a z-score and a p-value. The z-score is our material, it's our source material that comes from real world observations, characteristics of our data, characteristics of our study, like how much data we collected, 300 observations in our sample. But then it does get kind of brought together through an equation, a mathematical equation, that allows us to place it on this line and determine how many standard errors it is away from the mean. And based on the number of standard errors it is away from the mean is our criteria for judging our level of confidence in rejecting the null hypothesis or not. The smaller the p-value, the more confidence we have in rejecting the null hypothesis. In other words, the more evidentiary basis we have for saying the null hypothesis is incorrect. There's always some chance the null hypothesis is correct. We never have a p-value of 0. We might have a p-value, of, that's an equal sign, a p-value of 0.000035. And if Stata, for example, only reports that p-value out 3 decimal places, it might look like a p-value of 0, but it's not. Our p-value is never 0. Why? Because there's always the chance that we could see a black swan. Is anybody familiar with the metaphor about black swans? Take that as just a little bit of homework. Look up black swans. The idea is we can never rule out the possibility that a black swan exists, even if all the swans we've ever seen are white. Right? Because it's possible, right, that our quote unquote truth based on a whole history of observations is falsified by an empirical piece of evidence. What would that empirical piece of evidence be, even if we've seen white swans our entire life? Observing a black swan, right? So it's always possible that there's evidence out there that refutes the results that we've previously gotten. So our p-value is never 0. But the more evidence we have in an alternative hypothesis as opposed to a null hypothesis, the smaller and smaller and smaller that p-value is going to be. Giselle?
I know that you already went over this and we discussed it in my small group too, but I'm having a really hard time linking how you get from the z-score to the p-value. Like once you place the z-score on the line and you know how many, like how far away it is from the mean, what happens from there to get to the p-value?
Nothing outside of the fact that that tells you how much space is left. So think about it like a slider. Let me just put this back up one more time real quick. You know, let me see if I can get close enough in here. You know, if our z-score, let's say this is, right? Let's say this, let me get rid of this. Let's say this here is 2.42. Then what is the size of the area to the right of it in purple, right? Out here in this tail. The size of that is what did we say before? Somebody, anybody? 0.0078, right? So that's 0.78% of this entire area, right? Of this entire area, oh, it's coloring beneath. Of this entire area under this blue curve, right? This entire area under the blue curve, you know, equals 1, because that's the entire probability space. And so our z-score is going to be some distance away from the mean. And in this case, it's 2.42 standard errors. So as I said before, if this is 1 standard error, this is 2 standard errors, this is 2.42 standard errors away from the mean, right? And so what we know is that what's left under this curve over here that's in purple is 0.78% of this overall probability space. And that represents the likelihood of rejecting the null hypothesis when we shouldn't. That's not a perfect way of talking about a p-value, but if you need something that's maybe a little bit more concrete at this point, it's, you know, what is the likelihood of rejecting the null hypothesis when we shouldn't reject the null hypothesis? Now, again, if I went into a statistical discussion forum online with a bunch of econometrics professionals or statistical professionals, I'd be beaten for that. But I mean, just if you need kind of heuristic device in your head to think about, well, what does that mean? That might be it. Megan, go ahead.
I'm sorry, but could you explain one more time how you got the 0.0078?
Sure. So
Okay,
in this, yeah, absolutely. So in this, Z table here, right? We can go to, and again, I'm doing negative. Well, let's do it this way. So the z-score was 2.42. So I come down. In this first column, you get the integer value, the whole value, plus the tenths. So we go down to 2.4. Yeah? And then we need hundredths of 0.02. So we scroll over, right? Notice up here in the top, it's 0.02. So here at 2.4 and then 0.02 at that intersection is the equivalent of 2.42. You see that 2.4 here and then 0.02 here. So that's 2.42. Now notice, that gives us a p-value of 0.9922. But as I said, and I understand why this is a bit confusing, but just don't sweat it for now. We were doing a one-tailed test where we wanted to know if our observed value, right? Our estimated mean of 1272 is above a certain threshold, 1250. And so we would do 1 minus 0.9922. 1 minus 0.9922 equals 0.0078. A quick, which is how I did it in the solutions, a kind of like cheat sheet way to do that is to simply flip to the negative side, right? And go to negative 2.42 and you get 0.0078, okay? And if you didn't like my pictures before, look at this one, right? This Z table says that finding values on the left of the mean, we want to know how much probability space is to the left of our Z-score. So remember, our Z-score is somewhere along that x-axis. And we want to know how much of the probability space is to the left of that, is shaded in gray. And that's going to be a certain size. On the other side of the table, right, we have positive values of Z, right? Once we get past that midway point, we get positive values of Z, and those are associated with these scores down here, and that will tell us how much probability space is in gray to the left of the Z-score still. But of course, it's going to be a much greater amount because we're on the positive side of the distribution. Jeanette?
If the Z-score was, say, for example, 1.42, what changes would we expect to see?
If the Z-score was 1.42, then your p-value would be 0.9222.
Okay.
So then if you're still doing an upper tailed test, meaning that you're seeing if your observed mean is above a specific threshold, then you would do 1 minus 0.9222, right? And that would give you, what, 0.0, 0, what would that be? 0.0078? No, that's what it was a minute ago. Oh no, it would be 0.0788. So you would be above 0.05 in that case. So, well, I mean, the easiest way to find out is just to come here. Yeah, 0.0778. And so you're above 0.05, and therefore you fail to reject the null hypothesis, right? You don't have sufficient evidence to reject the null hypothesis at the 0.05 level because you're above 0.05, not below. Good question. And just to kind of think through that process, right? You would get that, you would get a 1.42 Z-score if you had different characteristics of your sample, right? If you had maybe a different sample size, or if maybe the difference between your observed mean and your threshold, your let's say 1250, the standard, was smaller, right? Because it would be essentially harder to determine the difference. I mean, think for a minute, if your observed value was 1253 and your threshold was 1250, it makes it much harder to determine that you're above the 1250, right? If the pollution level is 1253 and your baseline or requirement is 1250, it's much harder for you to make that determination, all else being equal, that you're above that line compared to if your pollution level was 1271 or 1295 or 1400, right? Then obviously there's a much bigger difference in your numerator between your observed mean value and the threshold or baseline value of 1250. So, when you think about that equation, I guess just think about that in terms of, the numerator is how big of a difference there is between your observed mean and your hypothesized mean, that baseline value or reference point. And the bigger that is, the larger your z-score will be. Whereas the bigger your denominator is, the smaller your z-score is going to be. The bigger your z-score, the smaller your p-value. And so let me just bring all of this home. Like I said, I told you I would connect this to what we're doing going forward, and then we'll move on to the final part of class. Let me pull this back up one more time, come to a different part here. So what we've learned in here so far is that we have a z-score, right? So that's z. You've also learned for today about a chi-squared statistic, right? This was for crosstabs, right? So this one was for univariate hypothesis test. And there are others, but that's a key one. A chi-squared statistic is for cross-tabulation. You're going to go on and learn a few more. You're going to learn a t-test. Well, a t-test has a t-statistic. And this is for a difference of means test. You'll after that learn the f-test with the f statistic. And that is for analysis of variance, what we'll call ANOVA. After that one, you're going to learn the R statistic. And this is correlation, and it's also used in regression. So here we have different statistics. Each of them has an equation, right? Each of them has its own equation. That equation represents the mathematical process that our data is run through in order to get to a p-value, right? And we use them in these different circumstances or these different scenarios, right? So this is the statistic that follows this, scenario, or I guess better put it would be the actual method. But all of them, right, all of these together are a means to an end, and that is a p-value. And the p-value, and we'll kind of process this more later, is a probability. And it's in particular the probability of observing, let's just call it your results for now. So the probability of observing your results by chance. And this is why if our hypothesis says that X causes Y, then we want our p-value to be really low if we think our hypothesis is correct, right? If we think our hypothesis is correct, then we want the likelihood of that hypothesis emerging in our data due to chance alone to be, we want that to be very small. Oh, I thought I was sharing my screen this entire time. Let me just share it real quick so you can see everything that I just wrote. There you go. Right, so we have all of these statistics. We have these different methods, right, that correspond to those statistics. And then these statistics you can think of as a means to an end, right? A z-score of 2.42 doesn't mean anything to you. Doesn't mean anything to anybody until you convert. Well, it does mean something to those of us who've been at this for a while, right? It's how many standard errors is the z-score, away from the mean, but or how many standard errors is it, different from the mean. And I guess the the point that you need to take away though is how does that translate into a p-value that gives you an indication as to whether you should reject or not your null hypothesis? Because it's the probability of getting the results that you did purely by chance, as opposed to being because of some systematic association between those two variables. Or in the example we just did, a systematic difference between our observed sample mean of pollution and our hypothesized or threshold value of pollution. You know, what's the probability of getting 1271 if the true value was 1250? That's what we really wanted to know there, right? What's the likelihood that we got 1271 as our estimated mean from a 300 observation sample if the true level of our pollution was 1250 or below? I see nodding heads, so let me say it one more time because I feel like that might have sunk into a few people. What is the probability, and this is what the p-value tells us, what is the probability, right, that we would have gotten a 1271 pollution level if the true level of pollution was 1250 or below? That's what we're really trying to, answer with our p-value. What is the likelihood of getting the results that we did due to chance? Okay, that will become, I promise you, clearer as we move into the bivariate tests. And so what I'd like to do is take a few minutes here to talk about cross-tabulation and hear what questions you have. We can do this very quickly because I do want to leave room for problem set 1 questions and answers. But let's just take a quick look at the Sexer and Furman article on crisis bargaining and nuclear blackmail and see why this is a good example of cross-tabulation, or why this represents a good setup for doing cross-tabulation. So go ahead and pull out Sexer and Furman, crisis bargaining and nuclear blackmail. We won't take as long on this one as we did the Moore and Shellman reading last time, but we will ask the same basic questions. What's the research question? What's the dependent variable and how is it measured? What's the independent variable and how is it measured? And I think by answering those questions, we'll know why this is a good representation of like a crosstabs type of study. So what is the research question for the Sexer and Furman article? Cynthia.
The question is, if a state has nuclear weapons, does it affect their coercive or ability to change behavior during an international crisis?
Fantastic. So that's right on the money. I now want you or someone to make that a why or a what explains question that focuses on the dependent variable, right? So you asked the question, frankly, better than they did, but it's still phrased in this kind of yes or no, right? Does it or doesn't it have an effective, kind of use? How can we make that a why or what explains? Jeanette?
I was thinking maybe like what explains the relationship between a country's nuclear possession and compliance of their demands.
Okay, I think that's really good and gets us very close. The one thing about that one is it assumes that it does have an effect, right? What explains the effect of this on this assumes that it does have one, and therefore it doesn't leave open the possibility of null results, right? That it doesn't have an effect. But I think otherwise your phrasing almost puts us there. Do you want to take another step? Anybody else? Neville?
What if we said something like, how effective are nuclear states at using their nuclear power when it comes to leveraging their demands?
So I think that works as a second question, right? A question that puts together a kind of potential cause, a hypothesized cause and outcome. But right now I want to focus purely on the dependent variable, right? What is the dependent variable? Let's start there. Meaning the outcome. Yeah, Cynthia?
Success of being able to change another state's behavior.
Yeah, exactly. Yeah, it's basic compliance, right? I mean, it's really, if you put it in terms of the agency of the militarized, you know, what would you say, the source, I'm trying to use their terminology here, you know, of whether a power or a state possesses nuclear weapons, then it's how easily can they obtain compliance, right? And so why do some adversaries in militarized disputes comply with challengers while others don't, right? If the dependent variable is compliance, then we want to know what explains variation in compliance. So before we even think about the cause, we want to think about the outcome. What explains the willingness of a target of a militarized dispute to comply with the demands of the challenger? Or to put it in a why question instead of what explains, why do some adversaries in militarized disputes comply with a challenger's demands while others don't comply, right? And so nowhere in there did we say anything about nuclear possession of the challenger. We didn't put forward our cause yet. And that's important because we want to be open to lots of different answers, right? After we ask the question, we go and do a literature review to figure out what possible answers there are. And then we try to theorize our own answer. So before we put forward some answer in our question, let's just ask the question about the variation in the dependent variable. Okay, what explains the willingness of a target of a militarized dispute to comply with a challenger's demands? Or why do some adversaries in a militarized dispute comply with the demands of a challenger while others don't? Great. So with that said, we now know that the dependent variable is possession of nuclear weapons. I'm sorry. We know that the dependent variable is compliance with the demands of a disputant, right, with an adversary. Amber?
Yeah, I'm just wondering if you could leave it at like, why do some states comply in military disputes, or do you have to be specific about like in opposition to X, Y, and Z?
I'll tell you the reason why I did it that way in those two versions of the question I asked is because the data set and their unit of analysis is about dyads.
Okay, that makes
right,
sense.
meaning a challenger and a target of the challenge.
Yeah, okay.
And yeah, and so I think a lot of times we want to see our unit of analysis represented in our question. Yeah, good, really good question. Okay, great. And so now what does this look like in terms of research design? The dependent variable we just said is compliance. How is that measured? What's the level of measurement or the type of variable? Jeanette?
It's dichotomous, so 0 and 1.
Fantastic. So we have a dichotomous dependent variable, 0 and 1. 0 is what and 1 is what?
Well, 1 means that the target voluntarily complied with the demands of the challenger, and the
Yes.
challenger did not have to use military force to achieve its desired outcome.
Okay, good. So 1 is that it complied in full with all demands. 0 is it did not comply in full with all demands. So then what's the independent variable? There are a couple of them. Or a few actually, but we'll do all three really quick. What's the cause? Brittany?
So one of the independent variables would be if the state demanding compliance had nuclear weapons.
Good. So we have nuclear possession of the challenger.
Did you want me to do the other two also?
Might as well.
Okay. And then if the state who they wanted compliance from, if they had possession of nuclear weapons, and then like, you know, if neither state had possession or like equal power.
Good, both. Yeah, good. Okay. So it's who has nuclear weapons, and does that affect whether a challenger is going to comply or not comply? I'm sorry, a target is going to comply or not comply with a challenger. So now, as I told you before, I think one of the best ways to think about research designs, you know, quantitative research designs, is to think about what it looks like in the data set. And so if you think about this data set, right, we get a spreadsheet. And we have our variables in columns, including our units of analysis. Okay, and then we have a bunch of rows. Okay, and then, as we've seen before, the rows are our observations and the columns are the variables. And so here we have dispute, right? So each dispute has a number. So we'll just say, you know, this is dispute 1, 2, 3, 4, 5, 6, 7, all the way down. There is a, you know, let's say state A, or the, you know, the challenger, and then there's a target. And then in each of these, we have the independent variables. Oh no, we need a dependent variable first. And then we have independent variable 1, independent variable 2, and then let's make one more. Whoa, because I want to show you what this, you know, what is happening here in terms of coding these variables also. I think it's kind of interesting just to see. Okay, and then independent variable 3. And what we know, right, is that independent variable 1, right, is nuclear possession of the challenger, right? So it's challenger possession. This is target possession, and this is both possession. And this is compliance. Okay. All of these, as we said before, are dichotomous variables. So now think about it like this. You have A and B, you know, A and B. Just imagine that all the way down. But at some point, right, you might get, you know, F and J, right, or whatever, right? We have a bunch of challengers and a bunch of targets. Now, what I wanted to show you is, right, the dependent variable is about whether there was full compliance or not full compliance. And so we could imagine having 0, 0, 0, right, like no compliance, 1, 0, 1, 0, 0, 1, 0, okay? Now this one over here, maybe we have that the challenger did have nuclear weapons or didn't have nuclear weapons. So it's didn't and did. Okay, now does the target possess nuclear weapons? Sometimes they do, sometimes they don't. And now in this third category here, right, whether both do, that's basically a function of whether the challenger and target both do. And so really that is just multiplying this by this, right? It's multiplying these two together. And so in Stata, let's just pretend for a minute, like we did last class, that we don't have this both possession variable, but we want to make a both possession variable. Instead of you going through here and looking across and having to put a number, you can just simply multiply one by the next. Multiply IV1 times IV2. And so this is does not, oh no, this one does, whoops, sorry. Because 1 times 1 is 1, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1, 0, 0, 1, 0, right? And so this gives us a whole lay of the land about who has nuclear weapons, whether it's challenger, target, or both, and who complied. If the hypothesis is correct that compliance is greater when the challenger has nuclear weapons, then there should be essentially a kind of correlation of sorts, although we're not talking correlations in crosstabs, but we should see that the dependent variable compliance is a 1 when the challenger is a 1, more often than not. Now, it doesn't mean that every time you have compliance, you have the challenger as a nuclear power, right? And it doesn't mean that every time you have non-compliance, the challenger isn't a nuclear power. But again, with our kind of broad, large number of observations, we want to see if, generally speaking, more often than not, to a large degree of confidence, compliance comes from challengers having nuclear weapons, right? Or when challengers have nuclear weapons, compliance is more likely. And since we have dichotomous variables, right, they're categorical. And when we have a categorical independent variable and a categorical dependent variable, we do cross-tabulation. So that's Sexer and Furman. And so now I just want to finish with two things, and we'll call this broad Q&A. Q&A about cross-tabulation, okay, since that was something that we looked at for today's class. We'll have more time to talk about it, of course. Or questions and answers when it comes to problem set 1. And so I'd welcome either of those. We have plenty of time to, I think, discuss the basics on those things. So lead us out. Any questions you have? Giselle.
So in the table that you were drawing right now, if we have the same challenger and the same target in multiple conflicts, do the variables change? Because we might not get the same results in compliance and possession of nuclear. Maybe in some of the conflicts they complied, in some of the conflicts they didn't, and it's the same challenger and target. So do we have to add something else for it to be relevant?
No, because the unit of analysis is dispute, right? And so the dispute is what ends in compliance or not. So you could have many different disputes between A and B, right? I mean, you think about, for example, you know, China and Japan in the South China Sea, or you think about, you know, what's been in the news recently with Israel and the Palestinians, in particular Hamas. And so you might have, for example, a dispute that's considered between Israel and Hamas separate than a dispute between Israel and the PLO. Or you might have multiple disputes that happen between those same two dyads, right? So the point is, their unit of analysis is militarized dispute.
Mm-hmm.
And therefore you can have many of those disputes amongst the same dyad. And the question is, was there compliance in the dispute, not was there compliance between the two states or the two entities in the dyad?
Okay, thank you.
Good question. Yeah, absolutely. That's why unit of analysis is so important. Okay, Anastasia?
I think Jeanette was before me, but I can go. So I have two questions. One is of administrative nature.
Yeah.
For section 1 of problem set 1, is it okay to provide an Excel sheet as an annex to kind of show the calculations, or do we have to implement this into the answers themselves?
No, go ahead and just provide an Excel sheet if you're doing it in Excel. If you did your work, you know, I know I say show your work there. You know, if it's a basic calculation, just, you know, you can just indicate what you did. Oh, I divided this by this, and here is the answer, or something like that. But yes, to answer your question simply, sure, provide an Excel sheet, show your calculations there.
Okay, so it's either or, like, or we have to do both.
Oh, you certainly don't have to do both. In fact, I might have even oversold how, you know, how much I need you to really provide there in terms of showing your work. I mean, some of those questions don't really require much work at all. And I don't want people to have to really struggle or go through the hassle of trying to kind of like write digitally on paper, other things. So whatever you can do to simply say, this was the calculation that allowed me to arrive at this answer, that's what I would like to see. So you can narrate it out, you can write it out, you can type it out, or you can provide an Excel sheet that shows that you did your arithmetic that way.
Okay, all right. And the second question I had was about the 1.5 times IQR formula. And my question is whether on the result, the plus or minus, not sure how to phrase this, but if on the range we include the values themselves, like the maximum and the minimum, or
oh, I see.
Like
so it's like, is it inclusive of the value that you get when you do 1.5 times IQR?
Yes.
So you know, that's kind of based on convention. You partly because it's not, you know, it's a manufactured rule, right? It's the 1.5 times IQR rule, but I mean, why isn't it the 1.45 times the IQR, right? Or 1.3 times the IQR? And that's because it's a rule of thumb. It's a basic heuristic. And so you could think about it as inclusive of, meaning 1.5 times the IQR gives you some number. Let's say it gives you 50, right? You could say, well, anything that is 50 or more would be an outlier, right? An extreme case. Or you could think about it as anything above 50 would be an outlier or an extreme case. Generally speaking, it's just greater than, not greater than or equal to. But I would take either because it's not that kind of well prescribed of a thing. You see it different ways in different textbooks and by different people.
Okay, great. Okay, thank you.
You're welcome. Jeanette?
With the tables, are we allowed to screenshot them from Stata and then paste on the problem set?
Please don't. Okay. I mean, that's not going to make or break your, you know, assignment, but I just think that it looks underdeveloped, right? To kind of take that Stata output and screenshot it. And so, especially at this point where the tables that you would have to create are so small and so few, that it should only take an additional, you know, 5 or 10 minutes for the 3 or 4 tables in the assignment to produce good looking tables in Microsoft Word or Pages or whatever you're using. So, so my preference would be to do that. I can show you how to create, you know, nice tables in, you know, coming out of Stata, and I will do that actually before problem set 2. But I think for right now, just make your own.
Okay.
And like I said, I'm pretty certain that despite answering the question that way, I will get people who screenshot their tables from Stata and put them in as their answers. And that, you know, is suboptimal, but it's not going to somehow, you know, be a devastating blow to your final product. What else? I mean, that kind of comes down to the general principle that, you know, I wouldn't do that because I want my final submission to be as clean and final looking and professional as possible. I'm kind of particular in that way. And I think other people should be too in a professional setting, but I'm also not mean. So I'm not gonna be like, how could you possibly, screenshot your Stata output and put it here? So please do though, just as a side note that makes me think of, there's no reason for you to put your Stata program code or your commands throughout your document. There's absolutely no reason to do that at all because you're putting it in an appendix at the end. Right? And I wrote up a quick little tutorial about how to do that in the discussion forum. But as a quick reminder, in case people are interested, and maybe this is an opportunity where I can show you just one other thing that may be of interest. If you're working here in Stata, and let's say you've done a bunch of stuff. So this is just kind of left over from before. We need to be working inside of a do file, right here. And this is where we should be doing our commands, right? Like this. And then we run those from here, right? And it can't because it's already defined. But let me just run a couple things again just to show you something. I'm just gonna pick some random stuff here to do. Okay. I do realize though that sometimes it feels just much more convenient to work in the command bar down at the bottom like I do in class, right? So how should you prepare to submit your do file as an appendix? A couple things. Number one, you can simply take all of this command history here in the left and paste it into your do file. So if you've been working in here doing a ton of work and it's not in your do file, you can just highlight all of this stuff on the left-hand side. So what I would do is hold the shift key, right? I would click the top one. I would hold the shift key and click down as far as I want to go. Now I could do that all the way to the bottom, but I would never want to include errors, first of all. So like this threw an error. So I would never want to do that. Right? Or if I accidentally spelled something wrong, generate, regime, right? Generate is unrecognized. I would not want to include that, of course. So I would highlight everything, but I would skip over that red. The way you can do that is by using Control to select individual things, right? So Shift will select everything between where you start and where you finish. And if you hold the Control key on your computer, you can click individual things and take them out or add them in. You see? So I'm holding Control right now, and I'm taking things out and adding them in individually. Right? Or I can do Shift, Control to select this one, and Shift, Shift, Control, and Shift again together. All right, so all of that said, you copy that. Go over into your do file and paste it. Now, I do not want to get a raw do file like this without you piecing out what belongs to which question. And you do that with comments. And you learned about comments in the Starting with Stata tutorial number 3, where you can use asterisks as one type. And so this might be question 3A. And then this one might be, question 3B, right? And so you can do that throughout here. And there are a variety of ways to do that. Sometimes you could, if you wanted, you could do it like this, question 3, right? And then just do A, B, maybe it's C, I, and then CII, right, and CIII. So however you want to break it down, but I should be able to look at your do file and know what belongs to what. So once you've created a good looking do file that's well organized and represents, essentially a walkthrough of your entire assignment, how do you get it out? Since you all are working in VMware, right, in the AU apps, all you do is in your do file, so first of all, save it as a do file, right? So file, save it as a do file, call it testing. And then after it's a do file, you need to do file, save as, and then pull this down and make it all files. Okay, change that to all files. And then at the end of your file name, do .rtf. RTF is a file type called rich text format, and that will open up in Microsoft Word or Pages or Google Docs or whatever. Okay, so testing.rtf. Click save, and then, and of course, save that onto your local files. And then you can go ahead and go into, your files. And find it and open it in Microsoft Word. I'm not going to do that now because it's a waste of time. But essentially, you'll go in and you can find it. Maybe I can do it. There, testing, right? So here it is. And it will open looking like this. And so now you can just copy this and paste it into your actual problem set document, right? Or you can put your problem set document above this one, whatever you like. Okay, but now this is in here and I can read it, and so that's good. Okay, what else? Jeanette?
So just to be clear, the appendix, you just want like the labels for the questions and the code.
Yep, exactly. Exactly. The labels for the questions and the code. And all of your answers are above as a report that doesn't have the code in it.
Okay.
Okay.
Because just for like I would put some notes in the, like when I was doing the
you
coding.
can keep your notes. Yeah, okay. Feel free. Absolutely fine. I just want to be able to replicate it, and I don't want a bunch of extra like junk in there of things that you tried that didn't work or things that were errors or whatever. But if you put notes along the way to keep your answers or what have you, then that's fine. Or just as reminders, or this is what I'm using. That's perfectly fine. Bethany.
Are all questions in section 2 used? Or some of it used from or found in the document as well, like the article?
I think there might be a couple of questions where you can find the answer in the document. When I ask like number of observations, certainly that's right there in Stata if you just use describe or something. But if you pull that from the article too, that's okay. I think the very first question I ask is about a relationship that's covered in the that's covered in the article. Like what's one of the main relationships that is discussed. And so that's just from the article. I think pretty much everything after that is kind of Stata driven. Make sure when you do your problem set that in that kind of report portion, that top portion, you include any tables and graphs. Jeanette mentioned this before, but I just want to make sure it's clear that if I ask you for a histogram, I don't want you to say like C do file for code. I want you to put the histogram, And so we talked before about how you can save a histogram, just once you produce any type of graphical representation of your data, you can save that. Right, so it's like hist health exp share GDP, and it'll create a histogram. It's over here, and this you can just do file, save as, right? Save it as a PNG file or a JPEG, either of those, right? This is, This is like Q5 graph, question 5 graph. Save it. And then you can, when you're putting together your report in Microsoft Word or Pages or whatever, navigate to where you saved it and then insert it as a picture. Just make sure that when you're saving it as, we discussed last class, and as we've talked quite a bit in the forum for people who are interested, that you need to, I'm not in VMware right now, so I can't, show you directly, but I did in a previous class session, where you scroll down to my computer, right, or this PC, and you'll be able to find on here a drive for the remote computer. Don't save it to the remote computer, or else it'll get wiped out when you log out. So make sure you save it to your local hard drive, your files there, okay? All right, good. Anything else from problem set 1? Anastasia.
Yes.
Anastasia.
Yes, thank you. And is that the same process to save tables, or does the table have to be screenshot?
I'm going to show you ways to produce tables later. I would prefer you not screenshot the table. I would prefer you make a table. Like, you create a table in Stata, it gives you this many rows and this many columns with this data in it. And then in Microsoft Word or Pages or wherever you're doing it, you create a table with that many columns and rows, and you type in the data so it looks nice and clean.
All right, thank you.
Drew, is that a question or not? Pencil flip. All right, very good. Okay, anything else? Yeah, Jeanette?
Sorry, just another question. Just for question 3.
Yeah.
So I was kind of given like the understanding that you could answer it, you can find the answer in different areas. Like you can either use Stata, the code book, or the article.
Yes, correct.
Okay.
And there are a number of, look, and even for the ones where you can only do it in Stata, I just want to make this clear for everybody, right? There are some, most questions you can only get the answers by working through Stata. But as we've seen in some of our practice, oftentimes there are multiple ways to do things through Stata. Maybe you want to use Codebook, maybe you want to use Summarize, maybe you want to do Summarize with Detail, maybe you want to, I mean, there are a number of different ways that you can often do things. There's a great command, I don't think I've taught you yet, but I will next week probably, called tabstat. And tabstat is a command that also lets you get descriptive statistics, just like Summarize. But instead of Summarize, Summarize gives you a bunch of statistics. The mean, the standard deviation, the minimum, the maximum, right? The number of observations. And sometimes you don't want all of those things. Or if you need more than that, like the median or the 5th percentile or something like that, you would do Summarize, comma, detail, and it gives you a whole bunch of other stuff. The tabstat command is cool because it only gives you what you ask for. And so, you can specify specifically what it is that you want, right? Like if I did tabstat polity, and then everything happens from the option. So you do tabstat, then the variable name, and then you do an S is the option for statistic. And then you can specify what you want. So I can put mean, standard deviation, variance, min, max. Let's do those. And it gives me just those things. I'll give you one that might be handy when you're doing, somebody asked before about the IQR, right? Anastasia was asking before about the interquartile range. Well, let's say I wanted that for the healthcare expenditures, right? I can just do QIQR and it gives me the quartiles and the interquartile range, right? Because Q and IQR are the statistics options that would automatically give me the quartiles and then 7.536926 minus 4.342947, which is 3.19398. Right, so it automatically does that subtraction for you to get the IQR. And of course, if you need help with that, you just do help tab stat. And you can see here that the statistics you can use, you can just do statistics and in parentheses, put any statistic name that falls in this list down here. And so you see, I just use Q and IQR. And that's how I got those. Okay. All right, that's the end of class. I'm going to stick around for a bit if people want to chat more about problem set 1 or anything else. If you're having computer-related troubles with Stata or anything else, please stick around too. It's absolutely imperative that you can, be operating smoothly within the software program so you can tackle, the practice problems, the problem set, the starting with Stata tutorials and that kind of thing. So with that said, and barring any further questions or comments, I'll say good night and have a great rest of your week. And feel free to use the forum. Actually, let me make that one last final point, and that is the forum is a place where you can consult about the problem set, right? I'm happy to see you all discuss the problem set if you like. As I said in the instructions to the problem set, though, you need to try everything yourself first. You need to answer all of the questions yourself at the end, right? But if you need some general consultation in the interim because you hit a roadblock or you just need some sort of help or support to get unstuck from something, then you're more than welcome to do that. I want you to do that, though, in the discussion forum, not in the WhatsApp group or something like that, number one. And that because it helps me see where are people getting stuck or what are the questions, and I can also chime in there. And there's no, no harm in doing that because I'm, right there. And I'm giving you permission to do that. So discuss the problem set, that's fine. Just make sure you're not sharing code, you're not sharing answers, right? You're not saying explicitly, this is how you solve this problem. Ask more general questions and provide more general support and feedback. So that way it helps the person, get unstuck or you get the support you need without, having it done in full for you, right? Or for somebody else. But feel free, if you want to start a thread on problem set 1 or specific questions within problem set 1, feel free to take it to the discussion forum. I've done that in lots of previous semesters and it always works out to be, I think, rather helpful. So with that said, good night, have a great rest of the week, and I'll stick around and chat with anybody who wants to stay. Take care.